All right, so let's get started. In this video, we are going to talk about uh, rotation. So we have talked about various aspects of rotation in previous chapters. So we've talked about rotation a little bit in chapter 3. We've talked about it in chapter 5. So some of the things that you're going to learn about in this chapter will seem familiar because you've heard about them before. All right, so now the first thing that we're going to discuss when we talk about rotation is the concept of the axis of rotation. So the axis is exactly what you think it is. It is an imaginary line about which the whole system is rotating. For example, if you have a bicycle wheel like in this picture here, the axis of rotation would be an imaginary line which passes through the center of the wheel and is perpendicular to the wheel. If you have a globe that's rotating, then the axis would be an imaginary line that passes through the north and the south poles, right? So the axis is nothing but an imaginary line about which the system rotates. Okay, now if an object is rotating, suppose you have an object that's going in a circle like this. If it's going in a circle, the radius is always fixed. I mean, the radius of the circle doesn't change. So the only thing that you need to keep track of is the angle that the object is making with respect to some reference direction. So suppose our reference direction is the x-axis and the object is over here. Then we only need to keep track of this angle. Right? So this angle that the object makes, that the radius vector of the object makes with respect to some arbitrary reference direction is called the angular, it's called the angular position. Okay, so theta here is our angular position. Now, suppose the object was initially at the angle theta 0, and then it moves to a new angle theta. So what is the change in its angular position? The change in its angular position is this angle right here, and we're going to call that delta theta. So delta theta is called the angular displacement. So theta is the angular position, and delta theta is the angular displacement. Remember when we talked about position and displacement in earlier chapters, the displacement was just the change in position, the initial position minus the final position, the final position minus the initial position. So here it's exactly the same thing. Delta theta is the angular displacement, and that is just theta final minus theta initial. All right. The next thing is the distance moved by an object as it's moving along a circular path. So suppose the object starts over here at point A and then it moves to point B. Its angular position has changed by an amount delta theta, right? How much distance has it covered along the arc of the circle? So what is this distance going to be? So we're going to call this distance delta S and let the radius of the circle be r. So if you know r and delta theta, what is delta S? The answer is delta S is given by r delta theta. And you might have seen this formula before. It is just the arc length formula. You might have seen it in the form S equals r theta, which is sometimes called the arc length formula. So we are basically just using the arc length formula, except that we are calling the angle as delta theta and the distance, the arc length, as delta S. Okay, now suppose the object moves through a very, very tiny angle. So suppose the object is, all right, so I'll just draw a different one. Suppose this is our circular path, and the object was initially over here at an angle theta, and then it changes its angle by a very, very tiny amount. So let this angle be called d theta, right? So you know that a very tiny change to a variable in calculus, we just call that d of that variable. So d theta means a very, very tiny change to theta, right? So how much, so what is the change in the, what is the distance moved by the object? So we're going to call this infinitesimally small distance as ds, right? And so what's the relationship between r d theta and ds? Using the same formula as before, ds is going to be r d theta. Okay, now ds is equal to r d theta. All right, so at the bottom of the PowerPoint slide, slide 3 of the PowerPoint, there's a question, what is the direction of ds? Now, going back to this diagram, the previous one, if I had asked you what is the direction of delta S, you would say that delta S is not a straight line, so there is no direction for delta S, right? It's a curved line. But if I ask you what is the direction of ds, then if you think about it, ds does have a direction. Why? Because I told you that the angle d theta is extremely, extremely small. So that means the two ends of ds are extremely close to one another, right? So on 2 points which are infinitesimally close to one another lie on the tangent to the circle, right? So that's pretty much the definition of the tangent. So ds is along in the tangential direction, right? So you can draw a tangent over here. You have to remember that ds is extremely small. The two ends of ds are practically next to one another. So the direction of the vector ds, you can think of ds as a vector, and its direction would be in the tangential direction, right? So ds is in the tangential direction. Okay. All right, but the same could not be said for a finite displacement of a finite angle delta theta. In that case, the arc length would actually be curved, and so it would not have any particular direction. This is only when the angle is subtended by the arc d theta is extremely small. Then you can think of it as being in the tangential direction. All right, now I'll talk a little bit about the arc length formula in case some of you might not be familiar with it or might have forgotten it. So this is a little aside on the arc length formula. So we say that S, the arc length, is equal to r theta. Oops, I should draw it over here. Okay, so S is equal to r theta. Now, in this formula, you should always remember that theta has to be in radians. If you use degrees for theta, you're going to get the wrong answer. So theta has to be in radians, right? And radians are unitless. They're pure numbers, right? Okay. So let's look at one example. So suppose theta, before we do that, suppose this is a circular track. The diagram that I have here is a circular track, and you start at this point A, right? And let's say that the radius of this circle is 3 meters. Okay, so r is 3 meters. Now suppose you start walking from A, and you walk a distance which is exactly equal to 3 meters. So along the circle, you cover a distance which is exactly equal to the radius of the circle, right? So you start walking, you have a pedometer, and you keep walking until your pedometer says that you've walked 3 meters, the same distance as the radius of the circle. So in that case, S is equal to R, right? And from the arc length formula, if S is equal to R, that would mean theta is equal to 1 radian. And that is pretty much the definition of a radian. So a radian is the angle subtended by an arc which is equal in length to the radius of the circle. So 1 radian is the angle subtended by an arc that is equal to the radius of the circle. Okay, that's the definition of a radian. And 1 radian is approximately 57.3 degrees, I think. All right. There is one other thing I can show you here. So suppose you start at A and you keep going all the way until you get back to A again. So you walk one full circle around the track. So you go around the track full circle. So what is the angle that you've traced out? So in that case, so if you do a full circle, the angle that you've traced out, theta, is equal to 2 pi, right? So what is the arc length that you've traced out? So S is equal to R times theta. So that's 2 pi multiplied by R. And that's exactly what you would expect. You get the circumference of the circle, formula for the circumference of the circle. Okay? So that's another example of applying this formula. All right. Now, on slide 4, I have a problem which is just an application of the arc length formula. So the problem is fully worked out on the slide, but the only thing that you have to be careful about in this problem is that when you apply the arc length formula, theta has to be in radians. So in this problem, you're basically you're given the radius of the circle, and somebody runs 1/4 of the arc, so 90 degrees. And what is the distance, arc length that they cover? So you would just use S equals R theta, but you have to remember that for theta, you have to use pi over 2 rather than 90 degrees. You would get the wrong answer if you do 90 degrees. All right, let's try the problem on slide 6. And once again, I would recommend that you pause the video at this point and think about this problem, and then we will get to then we will talk about how to solve it. Okay, so let's try the problem. So we are trying the problem on slide 6. All right. So what this problem is saying is that you're given the angular diameter of the moon. The angular diameter is a very common term in astronomy. What does it mean? So somebody's watching the moon from over here, and let's say that, and you can ignore the height of this person. Just imagine that they're a point mass on the ground. And there is the moon up here in the sky, right? The angular diameter would mean that you draw a straight line from the person's eye to one end of the moon, and another straight line from the person's eye to the other end of the moon, right? The angle between these two straight lines is called the angular diameter. Let's call it theta. And so theta is given to be 0.52 degrees in the problem, right? So this angle is the angular diameter. Okay. So you're given the angular diameter, and you're also given the distance to the moon. So the distance to the moon is 380,000 kilometers. And using these two pieces of information, you have to find out the physical diameter of the moon, right? Okay, now one thing that you can do is you could use the arc length formula to find the length of the arc between the two ends of the two opposite sides of the moon. So the length of the arc would kind of look like this. The arc joining these 2 points would kind of look like that. I don't need to have the edge over here. Okay. All right. So you could find that. Now, since this angle theta is extremely small, if you think about it, there won't be that much difference between the arc length and the straight line length between the two ends of the moon. So let me just call the two ends of the moon A and B. So if you think about it carefully, there's not that much of a difference between the arc AB and the straight line joining A and B, right? So if theta is small, then the arc AB is pretty much the same, is approximately the same as the actual distance connecting the points A and B, which is the diameter of the moon, right? A straight line distance between A and B, which is the diameter of the moon. So in that case, we could just use the arc length and call that the physical diameter of the moon, right? Arc length is very easy to find. S equals r theta. So r is 380,000 kilometers. Theta we have to express in radians. So to convert between degrees and radians, you use the fact that pi radians is 180 degrees, right? So that means 0.52 degrees would be 0.52 multiplied by pi divided by 180 degrees. So I'm just doing a unit conversion. So 0.52 degrees is equal to 0.552 times pi divided by 180. And if you work this out, you should get, let me see, okay, I'm just working it out here. So 380,000 times 0.52 so you get 3,449 approximately kilometers, which is a fairly good value for the diameter, fairly accurate value for the diameter of the moon, the physical diameter of the moon. So I want you to just appreciate for a moment the power of mathematics. So we are just sitting in our seats and we managed to calculate using two easily obtained pieces of information, the distance to the moon and the angular diameter of the moon. The distance to the moon is very easy to measure if you know how to measure it, and the angular diameter of the moon is even easier to measure. You can actually estimate it with your hands and fingers. Using these two very simply obtained pieces of information, you can actually calculate the physical diameter of the moon, which you might have thought would be impossible to measure from the Earth, but we can do it so easily. All right, okay. So the next thing that we're going to talk about is angular velocity. All right. So we were talking about an object that's moving in a circular path, and we talked about the angular displacement. So let's say that the object was initially over here, and then it moves over here and traces out this angle delta theta, right? Suppose this angle changes by delta theta in time delta t, right? Angular velocity measures how fast this angle at the center is changing, right? So the units of angular velocity are radians per second. So if the object changes its angle at the center by an amount delta theta in time delta t, you can define an average angular velocity, and the symbol for angular velocity is omega. This is the Greek lowercase w. So omega average is defined as delta theta divided by delta t. Right. Now, you know that we are not that interested in average quantities in this course. We are far more interested in instantaneous quantities. So I might want to know what is the omega at maybe t equals 5 seconds, or what is the omega at t equals 7 seconds. So in that case, what you do is you calculate the same thing, delta theta divided by delta t, but you make the delta t as tiny as possible. So if you want to know what is omega at t equals 5 seconds, then you want to consider a delta t, which is very close to 5, like which goes from 4.999 to 5.001, something like that. So the instantaneous angular velocity, which is what we are far more interested in, is the limit delta t going to 0, delta theta divided by delta t. And as you know from calculus, this is nothing but d theta dt. This is the definition of the derivative. So it's d theta dt. So this concept of instantaneous omega is very similar to the concept of instantaneous velocity that we talked about a long time ago back in chapter 2. So we get this very important relationship that omega is just d theta dt, the rate of change of angular position. Right? If the units of omega would be radians per second, right? And those are the units that we'll be using most of the time. If omega is constant, that is what we call uniform circular motion. So constant omega is uniform circular motion. So we had talked about omega briefly a long time ago, back in chapter 3, when we were doing a problem involving a vector problem involving rotational motion. And so we had talked about it at that time. And if you remember, I pointed out that omega measures how quickly the central angle is changing. And you can see that over here too. So that's exactly what it does. Omega is d theta dt. All right. Now, you might be surprised to learn that omega is actually a vector. You might have thought that it's a scalar, but it's actually a vector and it has a direction. So what is the direction of omega? So to find the direction of omega, what you do is, just get rid of this. So to find the direction of omega, you use the right-hand rule. How does the right-hand rule work? So you curl the fingers of your right hand in the way that's shown in the diagram. And then you, okay, just one second. Yeah, you curl the fingers of your right hand the way it's shown in the diagram over here. And then your thumb will point in the direction of omega. So for example, if you curl the fingers of your right hand in this direction, then your thumb, you'll find, is pointing in the direction of the arrow shown, right? I can show you another example. Suppose an object is moving in a circle like this, right, in the counterclockwise direction. So if you curl the fingers of your right hand in the counterclockwise direction, you'll see that your thumb is pointed out of the page, right? And so that is the direction of omega in this case. So omega would be out of the page in this example. And if an object is moving in the clockwise direction, then omega would be into the page in this example. So let's look at another example. suppose you have somebody riding a bicycle. Let me see if I can draw a bicycle. Okay, so it needs handlebars, it needs a seat, and okay, so it's looking pretty good so far. I should probably, all right, so now okay, all right, so it's missing the paddles, but it's okay. So here is our bicycle, and let's say that the person is moving in this direction. So that means the wheels of the bicycle are turning like this. The wheels of the bicycle are turning like this. So the bicycle is moving to the moving in the forward direction. The wheels are turning the way shown, right? What is the direction of omega of the wheels of the bicycle? So the way you would do it is you would curl the fingers of your right hand in the same direction in which the wheels are turning, right? And so the wheels are turning counterclockwise in this example. So that means the direction of omega is out of the page. And so the direction of omega would be to the left of the person riding the bicycle, right? So omega would point to the left of the cyclist. Okay. All right. So if you have trouble understanding this, you can ask me during the office hours, and I can try to show it to you using over the video. But yeah, so that's that. So what we have so far is an object moving in a circle, and let's say that it moves from this point to this point, A to B, and the angle that it traces out is delta theta. All right. Time it takes to trace out this angle is delta t, right? The arc length that it covers, which is the physical distance that it covers on the circle, is delta s. Now, what is the speed at which the object is moving along the circular path? So that would just be, you can just call that v average, would just be the distance divided by the time, right? What is the instantaneous speed? So what is the speed at one instant of time, like t equals 7.3 seconds or t equals 15.6 seconds? So for that, you need to take the limit as, so v would be limit as delta t tends to 0 of delta s divided by delta t. This is nothing but ds dt by the rules of calculus. This is just the definition of the derivative. Now, a result that we derived earlier was that ds is equal to r d theta. So this is r d theta divided by dt. And you can see that this is a vector because ds, we had discussed earlier, is a vector. It's in the tangential direction, right? If the 2 points A and B are very, very, very close to each other, then the line joining A and B lies along the tangent to the circle. So ds is in the tangential direction. And so V has a direction which is in the tangential direction. So lies in the, or I should say points in the tangential direction. And we can do one more thing here. We know what d theta over dt is. It's just omega. So we get V is equal to r omega. So what does V stand for? It's just the velocity of the object as it's moving along the circular path. V is exactly the same velocity that we've been discussing throughout this course. So there's nothing new about V here. We just call it tangential velocity. We just give it a new name, tangential velocity, to distinguish it from the angular velocity that we have also learned about in this chapter. So that's why we add tangential to the name velocity, but it's exactly the same velocity that we've been using in previous chapters, right? Okay, all right. So let's look at an example. me just pull up the PowerPoint. Yeah, so let's look at an example where we apply all these. So this problem in slide 9 is fully worked out on the slide, but we might as well just go over it. So this is the problem on slide 9. Okay, so in this problem you've got this amusement park merry-go-round, which you can think of it as a disc, and there are two horses. One of them is 3 meters from the center and the other one is 6 meters from the center. Okay, let's call this one as A and this one as B, and the whole merry-go-round is rotating. Okay, it's completing one, it's doing one complete rotation in 45 seconds. All right, so the question is, what are the angular speeds and tangential speeds of each child, of the child on the horse A and the child on horse B, right? Now, for the angular speed, you will notice that everything on this disk has exactly the same angular speed, because if one moment later the horse A is going to be over here and horse B is going to be over here, right? So they're rotating in exactly the same way. The angle that they're tracing out at the center is changing at the same rate for everything on this disk. So everything has the same angular speed. So angular speed, which is omega, is the same for every part, every point, I should say, of the disk. Okay. So how do we find that omega? Omega is just the angle that it traces out divided by the time, delta theta over delta t. So we know that it traces out a full circle, which is 2 pi, in 45 seconds, 2 pi radians in 45 seconds. So that's, if you just work that out, that comes to 0.14 radians per second. And so that's the omega. And that's the omega for both A and B and for every point on the disk. All right. Now, what about the tangential speed of each child? So tangential speed or tangential velocity is just the velocity of the horse, or A and B. So if both A and B had speedometers, then that's the speed measured by those speedometers would be what we call the tangential speed. So the tangential speed or tangential velocity is the same thing as speed and velocity that we'd studied from the beginning of the course, right? So how do we find the tangential velocity of A? We just use the formula V is equal to R omega, right? So the R for A is 3 meters. Omega is 0.14 radians per second. Remember, radian is a pure number. So radian is not any unit, it's just a pure number. So it's really 0.14 per second, right? So if you multiply these, you get 0.42 meters per second, which is exactly the unit you would expect for a velocity or a speed. So that is the speed at which A is moving, right? What about the speed at which B is moving? So that's going to be radius of B multiplied by omega, which is going to be 6 meters multiplied by the same omega, 0.14 radians per second. So that's going to be 0.84 meters per second. So you can see that B is moving at twice the speed as A, because B is twice as far, right? All right, so that's that question. The next thing that we're going to talk about is angular acceleration. So if an object is not executing uniform circular motion, which means that its angular velocity is increasing or decreasing, we can define an angular acceleration as follows. So we'll first start with an average angular acceleration, and then we'll move on to an instantaneous angular acceleration. You'll see that our discussion is very, very analogous to the way we defined position velocity and acceleration back in chapter 2, right? So now we have a situation where omega is changing. So let's say that the change in omega is delta omega. So what's an example of something moving where the omega is changing? So if you've ever seen a fan, you switch the fan on, then at first the fan is not rotating, right? So its blades are at rest, but then it starts speeding up. So that's an example of something that's rotating and speeding up. So the fan speeds up to its operational speed, and then it rotates, executes uniform circular motion because it keeps rotating at the same speed. And then when you turn it off, then it starts slowing down and eventually comes back to zero speed. So at that time, it's decelerating, right? So we are talking about the situation where an object is not moving at constant omega, but it's speeding up or slowing down, right? So the average angular acceleration alpha, so the symbol for angular acceleration is alpha. So alpha average is equal to the change in the angular velocity divided by the time it took for that change to happen, right? So that's the average angular acceleration. And its units would be radians per second divided by seconds. So it's radians per second square. All right. Now, we are usually interested in the instantaneous angular acceleration, which is the angular acceleration at a particular moment of time. So that is defined in exactly the same way. The instantaneous angular acceleration would just be the limit delta t tending to 0, delta omega divided by delta t, which is nothing but d omega dt. So alpha is just the derivative of omega, right? So alpha is equal to d omega dt. All right, so that's angular acceleration. Similarly, we can also talk about a tangential acceleration. What is that? So we have an object that's moving in a circle, and let's say it's speeding up. So it has a certain, it had a certain omega when it was over here, and now it has a greater omega because it's sped up, right? So if it's speeding up along the circle, then that means there must be an acceleration in the tangential direction. So if you measure the tangential component of its acceleration, there must be some acceleration in the tangential direction, which is responsible for it speeding up, right? So that acceleration in the tangential direction is called the tangential acceleration. So how do you define the tangential acceleration? It's just the derivative of the tangential velocity. So at is equal to dv dt. Now we have a formula for the tangential velocity, which is r omega, right? So if you plug that in, so this is d dt of r omega. R for a circle is constant, so you can pull that out of the derivative. So it's r times d omega dt. That's our tangential acceleration. And d omega dt is just alpha, right? As we saw a moment ago. So d omega dt is just alpha. You can plug that in. So a tangential is equal to r times alpha, right? This is a very important formula. So this formula and v is equal to r omega are both very, very important. So this is the relationship between the tangential acceleration and the angular acceleration alpha, right? So just to make that clear, what is alpha? So we have our object going in a circle like this, and it's speeding up or slowing down. Alpha just measures how quickly omega, the angular velocity, is changing, right? So omega is again the rate at which the angle made at the center is changing. So how quickly is the omega changing? That is measured by alpha, right? And A tangential is simply the tangential component of the object's acceleration, right? So the speed that it has over here is different from the speed that it has over here. Its tangential speed over here might be, say, 2 meters per second, and its tangential speed here might be 5 meters per second. So since its speed is changing, in the tangential direction, there must be some acceleration in the tangential direction, and that is what we call tangential acceleration. So the relationship between tangential acceleration and angular acceleration is this: A tangential is equal to R alpha. So please make sure that you understand what all these different accelerations are, like what is angular acceleration and what is tangential acceleration. Okay, now what would cause the tangential acceleration? There is a tangential acceleration because there must be some force in the tangential direction. Remember that any acceleration is caused by a force. Force equals mass times acceleration, Newton's second law, right? So that means if an object has a tangential acceleration, there must be some force in the tangential direction. So let's look at an example of that. Suppose you have a pendulum, a piece of thread, and you've attached a mass over here, and you swing it to one side and let it fall. So you know that when you release it from somewhere over here, it will start with 0 velocity, but by the time it gets over here to the bottom, it will be moving pretty fast. So that means it's speeding up as it goes on this circular path, right? So there must be some acceleration. Now let's see if we can figure out what is causing the tangential acceleration here. So this is the circular arc. Let's draw all the forces that are acting on this pendulum, right? So for example, what are the forces acting on it? There is gravity acting in this direction. I'll just use a different color for that. There's gravity acting down like this. There is the tension force acting in this direction. Now, we talked about how when an object moves in a circular path, there has to be the best way to break up the forces is in the radial and the tangential directions. So we talked about that back in chapter 5. So the tension force is already in the radial direction. Mg needs to be broken into two components. So we'll make one component of Mg which goes in the radial direction and another one which goes in the tangential direction like this. And let's call this angle theta. So this component is mg cosine theta, and this component is mg sine theta. So you can see that mg sine theta is a force component that's in the tangential direction, right? And so from there you can easily figure out the tangential acceleration by just using mass times acceleration. Force equals mass times acceleration. So Newton's second law in the radial direction Newton's second law would be the sign convention that goes with this choice of forces is radially inwards is positive. So that means T minus mg cosine theta is equal to mass times, what acceleration should I use? The object is moving in a circle, so I should use the centripetal acceleration. So if its velocity at that instant is v, so it would be mass times mv squared over r, right? So I just call that as mac, where ac is just v squared over r. And in the tangential direction, there's only one force, which is mg sine theta, and that is equal to mass times a tangential, right? And so from here you can easily figure out the tangential acceleration. At is just g sine theta in this particular example, right? So this is just an example to show you how an object can have a tangential acceleration and what causes that tangential acceleration. It's basically just a force acting in the tangential direction, right? Okay, so remember that an object can have a tangential acceleration if it's speeding up or slowing down, But remember that for the object to be on a circular path, it has to have a centripetal acceleration. So the centripetal acceleration is absolutely essential. So if an object is moving in a circular path, it has to have a centripetal acceleration. And then if it's speeding up or slowing down, it will have a tangential acceleration, right? So there are two accelerations that could be associated with an object in circular motion. The essential one is the centripetal acceleration, which we had studied a long time ago. And that is essential for an object to be moving in a circle. Right? It has to have a centripetal acceleration. Now, if the object is moving in a circle and also happens to be speeding up or slowing down, then it will have a tangential acceleration, which is responsible for the speed up or slowing down. So these are two accelerations that an object executing circular motion might have. The centripetal acceleration is essential. The tangential acceleration would be there if the object is either speeding up or slowing down. All right, so what we've seen so far is that an object that's rotating is guaranteed to have a centripetal acceleration. And if it's not uniform circular motion, like if it's speeding up or slowing down, then it will have a tangential acceleration. If an object has both centripetal and tangential acceleration, then the total acceleration of the object, so here's the object going in a circle. It has a centripetal acceleration which points towards the center of the circle, AC, and it has a tangential acceleration. If it's speeding up, let's say, it has a tangential acceleration speeding up in the counterclockwise direction. So its tangential acceleration would be tangent to the circle like that. So let me just draw a nicer diagram. Let me just make this really tangential. So what is the total acceleration going to be? So I'm going to write the total acceleration as A. So A, the magnitude of A will just be AT squared plus AC squared. Right? Because AT and AC are just two components of the acceleration vector. And so the magnitude of the acceleration, the total acceleration, would just be AT squared plus AC squared. And the direction of the total acceleration vector would be the vector sum of these two components, which is kind of in this direction. All right, so that's the total acceleration. Okay, now let's do a problem which illustrates all of these ideas, right? So we're going to give this problem a try. All right. So this is the problem on slide 14. Oops. Okay, so you've got a pendulum which has a bob of mass 1 kg, and it's suspended by a very light thread, and you're given the length of the thread, and it's swinging in a vertical plane, right? So the pendulum is released from rest from a horizontal position, and when the thread makes an angle of pi/6 with the vertical, so right now the pendulum, let's say, is like this, with this angle being theta, which is given to be pi/6, then the speed of the bob is 2.06 meters per second. So if we were in class, I would have asked you, which speed, what velocity is this 2.06 meters per second? Like, what would that be? Which velocity is that? Is that the tangential velocity, the angular velocity? What is that? Obviously, it's the tangential velocity. So the tangential velocity V is 2.06 meters per second, right? So, so the tangential velocity V is equal to 2.06 meters per second. Okay, so that answers half of the first question. What is the bob's angular velocity and tangential velocity? We already know the tangential velocity. How do we find the omega of the bob at this particular instant? So for that we use the relationship V is equal to R omega. So omega is equal to V divided by R, which you can easily calculate. It's 2.06 divided by R is the length of the thread, which is 0.25. So that's going to be, if I did my calculations correctly, that's going to be 8.23 radians per second. You can see how the units work out. This is meters per second, and this is meters. So meters and meters cancels out, and so you have per second, which is the same thing as radians per second. All right, so that's part one. So part two is asking for the bob's centripetal acceleration. So how do you find the centripetal acceleration? For that, what you can do is just use the same formula that you've been using for a long time now. So the centripetal acceleration AC is just V squared divided by R. So V is 2.06 squared divided by R, which is 0.25, and if you work that out, you should get 16.97 meters per second. Okay, so I'm just copying the answer that I already have on the slide. If we were in class, I'd have you double check the answer, but please do it and see if you make sure that you get this answer. All right, so question number 3 is, what is the bob's tangential acceleration? So the centripetal acceleration points towards the center of the circle, obviously. The centripetal acceleration would be in this direction. And since the bob is speeding up as it's going downward along the circle, it also must have some tangential acceleration, because this V, 2.06 meters per second, would not be the same. It would keep increasing, right? So there has to be some acceleration in the tangential direction, and that's AT. So AT, how do we find that? So to find AT, we would have to do a calculation very similar to what we just did a little while ago. And just for your convenience, I'll just do it once again in the context of this problem. So we have, let's consider all the forces that are acting on the bob of the pendulum, right? So what are the forces? The forces are, one of them is gravity. Then you have the tension of the rope in this direction, right? Okay, those are the only two physical forces acting on the bob, and it's tracing out this circular arc. So we've discussed how when an object is going in a circle, you have to resolve the forces into radial and tangential directions, right? The radial and the tangential directions are the best directions that you can use for resolving forces. So the tension T is already in the radial direction. So mg is the only thing that needs to be broken into two components. And so let's go ahead and do that. You can make one component which lies in the radial direction like this, and another component which lies in the tangential direction like that, right? And this angle is given to be theta, so that means this angle is theta. So that means this component will be mg cosine theta, and this one will be mg sine theta. All right, so now let's write down Newton's second law in both the radial and the tangential directions, right? So in the radial direction, this is exactly similar to what we did a little while ago. So in the radial direction, we are going to choose radially inward is positive. So that means T minus mg cosine theta is equal to mass times the centripetal acceleration. So that's going to be equal to mv squared divided by the r is really L in this case. So you can either do r or L. And in the tangential direction, so that's the equation we get in the radial direction. In the tangential direction, we get, there's only one force, so that's mg sine theta, and that must be equal to mass times the tangential acceleration, right? Just Newton's second law, force equals mass times acceleration. What we are solving for here is the tangential acceleration, so clearly that's just equal to AT is just equal to g sine theta. And that is the answer to part 3. AT is just g sine theta in this particular case, right? So you can just plug in all the numbers and work it out. So AT would just be 9.8 sine of pi over 6, whatever that works out to. Sine 30 is 1/2, so it's half of 9.8, so that's 4.9 meters per second. All right, meters per second square. That's the tangential acceleration. All right. Then the next question is asking for the angular acceleration alpha. So once you know A tangential, you can easily find alpha. So for part 4, the relationship between alpha and A tangential is A tangential is equal to R alpha, right? So you can easily solve for that. A tangential is 4.9. The radius, which is the length of the pendulum, is 0.25 alpha. So you can just solve for alpha from there. Let's see what I got. 19.6 radians per second square. All right. Then the question number 5 is the magnitude of the total acceleration. So if you know the centripetal acceleration and the total acceleration and the tangential acceleration, the magnitude of the total acceleration will just be AT squared plus AC squared, square root of that, as I just discussed a little while ago. And the last one is the tension in the cord. That is just a Newton's second law question. Going back to the radial component of Newton's second law, we got this equation up here, which was T minus mg cosine theta is equal to mv squared over L. So T minus mg cosine theta is equal to mv squared over L. So you can, from here, you can just solve for the tension. T is equal to mg cosine theta plus mv squared over L. And you can just plug in all the numbers and get the answer. So hopefully this problem clarifies all the different all the different quantities that we have discussed so far. All right, so please make sure that you fully understand this question. There is another problem which if you understand this question, you should be able to do it quite easily. But it's kind of on the harder side. So if you want, you can skip this particular problem, or you can give it a try. Yeah, but if you want, you can just skip this problem. Okay, the next thing that we're going to talk about is kinematics for angular motion. Okay, so let's talk about that. Angular kinematics. If you think back to chapter 2, we saw that, okay, before we talk about that, let me just talk about one other thing. So there is an analogy, there's a nice analogy, and you might have noticed it, but I'll just make it clear now. There's a nice analogy between linear quantities and angular quantities. So, okay, let's consider position. In the one-dimensional linear world, position was measured by, or if you just think of a object going in a circle, then the linear measure of its distance traveled, which is basically the arc length, was s, and the angular measure of its change of position was theta, right? And the relationship between them is s equals r theta. All right. Now if you consider how fast the object is moving along the circle, the linear measure of its speed would be the tangential velocity. The linear measure of its velocity would be the tangential velocity, and the angular measure of its velocity would be the angular velocity, omega. And we saw that the relationship between these two quantities is v is equal to r omega, Then if you consider how fast the velocity is changing, or if you move on to acceleration, the linear measure of its acceleration is a tangential. So a tangential measures how fast v is changing, right? And the angular measure of its acceleration would be the angular acceleration alpha. And these quantities are related by a tangential is equal to r alpha. So you can see that there is this nice analogy between these linear quantities which we had studied in earlier chapters and the angular quantities which we learned about in this chapter, right? Okay, now, okay, so this table actually goes on longer than this, but we're going to come back to this table later on. But for now, let's recall one other thing from when we studied position, velocity, and acceleration in chapter 2. We saw that if the acceleration is constant, then the position and the velocity and the acceleration are connected by simple algebraic equations, which we call the kinematic equations. You can do the exact same thing with angular velocities. So if the angular acceleration alpha is constant, then you can write down the angular kinematic equations. And what are these angular kinematic equations? You can actually write them down, even if you haven't learned this, you're learning this for the first time now, you can write them down in complete analogy to the linear kinematic equations, right? So instead of theta, instead of position, you're going to use theta, the angular position. Instead of angular velocity, you're going to use, instead of velocity, you're going to use angular velocity, I mean. And instead of acceleration, you're going to use angular acceleration. So let's see if you can just see if you can write down the first kinematic equation, which was v final is equal to v initial plus acceleration multiplied by time. So in the angular version of that would be omega final is equal to omega initial plus alpha t, right? So that is the first kinematic equation. The second kinematic equation would be theta final is equal to theta 0 plus omega 0 t plus half alpha t squared. Notice that this is just the first kinematic equation, the second kinematic equation with angular variables substituted instead of the linear variables. And what about the third kinematic equation? Omega square is equal to omega initial square plus 2 alpha theta minus theta 0. That's the third kinematic equation. So these are your kinematic equations. In problems, we usually just care about the angular displacement, theta minus theta 0, right? So unless an initial theta 0 is specified, you can usually choose theta 0 to be 0. Right? Okay, that's like in chapter 2, I told you that you can choose your x equals 0 wherever you want, x equals 0 and y equals 0 wherever you want. So same thing applies over here. Unless a particular theta 0 is specified, you can choose the theta 0 to be 0. Right? So let's look at an example of angular kinematics. So we will try the example on slide 17. So it says that a microwave oven has a 30 centimeter diameter rotating plate. The plate accelerates from rest at a uniform rate of 0.87 radians per second square for 0.50 seconds before reaching its constant operational speed. So how many revolutions does the plate make before reaching its operational speed? All right, so let's first think about what we are given in the problem. So what is this 0.87? It is clearly the alpha, the angular acceleration. So alpha is 0.87 radians per second square. Okay, and the time t is 0.5 seconds. Okay, so how many revolutions? So we need to find out how many revolutions the plate makes before reaching its operational speed. We are given the radius of the plate. Okay, so the radius is actually the diameter of the plate is given. So the radius of the plate would be 0.15 meters, because half of the diameter. Okay, so how many revolutions does the plate make before reaching its operational speed? Do we know the final? Yeah, so we don't know what the final operational speed is, but we could easily find that. So what is the initial omega? So the initial omega, the plate is starting from rest, so the initial omega is 0, right? And we want to find out what is the final omega. Let's go ahead and find that first. So the final omega is equal to omega 0 plus alpha t is our first kinematic equation. So omega 0 is 0, alpha is 0.87 multiplied by 0.5. So that would just be 0.87 times 0.5. It looks like I did it a different way on the slide, but we are just gonna do it the way we're proceeding now. So it's 0.87 times 0.5 is 0.435. So 0.435 radians per second is the final omega, right? So we have to find out what is the how many revolutions does the plate make before reaching this operational speed. So how do we find? So basically we are looking for a theta, right? So we are looking for what is the total angle it traces out, and then we can convert that into revolutions, because each revolution is 2 pi radians. So to find that, the final theta, we could just use this kinematic equation. Theta final is equal to theta initial plus omega 0 t plus half alpha t square, right? So theta 0 you can always take to be 0. Omega 0 is also 0. So that means the final theta would just be half times 0.87 times 0.5 square. And that would just be 0.018. No, actually, that would, let's work that out. So let's work that out. So half times 0.87 times 0.5 square is 0.10875. Point 1088 maybe 1088 radians, and we want to turn this into revolutions. So to make this into revolutions, we would just divide this by 2 pi, and that gives me 0.017. Is that what I have on the slide? Yeah. So 0.018 revolutions, right? So that answers part A. We didn't quite need the omega, but that's fine. I think we're going to need that in the second part. So this answers part A. Part B is asking what is the final operational speed. So we already found that. So that's 0.44 radians per second approximately. And what is the tangential speed of its rim? So to find, so for part B, we just use this. And for the tangential speed of the rim, we can just do V is equal to R omega. A point on the rim is at a distance of 0.15 meters from the center, the radial distance, the radius of the rim. So it's just going to be 0.15 multiplied by omega, which we just calculated, which is 0.44. So this is meters, this is radians per second, and this gives 0.066 meters per second. Okay. So as you can see, these kinematic problems are very simple. They're just like the simple one-dimensional kinematics problems that you saw in chapter 2, right? Okay. There's another problem in slide 18. Let's see if we can work through that one. Okay. So a bug is hanging on to the end of a fan blade of radius r, which was initially at rest, but starts speeding up with a constant angular acceleration alpha. Find the total acceleration of the bug at time t. So we want to find the total acceleration, right? So the total acceleration has two components. One is the centripetal acceleration and the other one is the tangential acceleration. So that's what we need to do. We need to find both components of the acceleration, and then we can find the total acceleration, right? So let's see. So here is the blade of the fan, maybe. I'm just drawing one blade of the fan. And here is the bug. Okay, so the bug is rotating. It's going in a circle like this. It's tracing out this green circle. And its angular acceleration is alpha. So let's see if we know the radius. The radius is r. So can we find the tangential acceleration? The angular acceleration is given. So a tangential is just going to be r times alpha. Right? So we have a tangential. And okay. At time t, what is the centripetal acceleration? So we want to find out what is centripetal acceleration. We want to find AC at time t. So how do we do that? So the formula for AC, as you know, is v squared divided by r. And v is equal to r omega. It's going to be capital R in this case. And v is going to be r omega. Divided by r, right? So that's omega squared times r. So I need to know what the omega is at time t, right? So I can use a kinematic equation for that. So I know that omega was 0, the initial omega was 0. The angular acceleration is alpha. So what is the final omega? So omega final is equal to omega initial, which is 0, plus alpha times t. So it's just going to be alpha multiplied by t, right? That's my omega final at time t. So I can plug that in to get AC. So AC is going to be alpha t squared multiplied by r, right? So alpha squared t squared multiplied by r. And then the total acceleration is nothing but, so I know what AT is, I know what AC is. So the total acceleration is going to be square root of AT squared plus AC squared. So that's going to be r squared alpha squared, oops, r squared alpha squared plus alpha squared t squared r, and this whole thing squared, and then the square root of that. Okay. All right. So that concludes our discussion of all the angular variables and angular kinematics. The next topic that we will talk about is rotational inertia.